And what we have now, we have written down the more general form of Schrodinger wave equation for an electron that's revolving around the nucleus, and under the combined effect of under the combined effect of the potential that's created by the nucleus and rest of n minus 1 electrons. So here, what we can say is that we have this Schrodinger's wave equation, and this zeta nl ml of r, they are basically the individual electron spatial orbitals, which are basically the representatives of the product of a radial function and the spherical harmonics. So we can write down this wave function. We can write down this wave vector as zeta nl ml of r into r of nl of r, and spherical harmonics psi y l ml theta and phi. So what we have here, we have the radial part and we have the spherical harmonics. So we can rewrite the Schrodinger's equation as minus h cross square by 2m del r square plus v of r times r and l y l m l theta and phi is equal to E n l r n l of r and y l m l of theta and phi. So what we can do here is that this kinetic energy, it does not depend upon theta and phi. We already understand from the problem of central potential that that the Hamiltonian it commutes with the orbital angular momentum operator, and if it commutes with that, then the terms that we'll have for spherical harmonics, they will simply represent the constants. So we can eradicate this part of spherical harmonics from Schrodinger's wave equation. So we can divide. So dividing both sides by y l ml theta and phi. So what we'll be left with is we will have minus h cross square by 2m del r square plus v of r times r and l equals E and L R and L of R. All right. So what we are left with here is we are left with the radial part of the Schrodinger's wave equation. So what is important here is that the kinetic energy, it does not depend upon theta and phi. So when it doesn't depend on theta and phi, and V of R is also central in nature. This V of R is central in nature now. So Schrodinger's equation can be reduced. It can be boiled down to the radial part. And writing down its solution in spherical polar coordinates. So what can we think of doing here is we would like to write down this radial part of the Schrodinger's wave equation, and would like to write down this in spherical polar coordinates first. So if I write down it in spherical polar coordinates, what I'll have minus h cross square by 2m times t2 by tr2 plus 2 by r t by tr minus l into l plus 1 divided by r times r and l of r, and then plus v of r times r and l of r. This is equal to E and L r and l of r. Okay, so this is basically the representation of a simple radial Schrodinger's equation of an electron in central field. In central field. And here, what we define n, and n is what? N is the principal quantum number. Principal quantum number, and such that this n is nr plus 1, nr plus l plus 1, and this nr is the representative of the nodes. So the nodes of radial wave function, nodes of radial wave function. And the quantum numbers, as usual, I mean, we have n and the numbers that are linked with n. So n can be 1, 2, 3, and so on and so forth. And then we can have L, and L is 1, 2, 3, so on and so forth to n minus 1, and finally we will have ml that goes from minus L to plus L. So, in central field radial orbitals, I mean, central field radial orbitals should not be confused with hydrogenic wave functions. It should not be taken exactly in the same way as we take the situation in case of the hydrogenic atoms, where we have the wave function psi nl ml of r. And as here, radial orbitals, what they do is that they depend on the choice of the central potential, V of r. So we should not take the equation here exactly in the same way as it is in case of hydrogenic atoms. So here you have to decorate, you have to design the central potential for particular problem. And what we have here is that in central field approximation technique, it seems to be unique solution deal with n electron atoms. I mean, the only issue in the application of this technique is the determination, or I should say the development, or I should say the fabrication of a form of this effective potential. Effective potential. Effective potential, and this effective potential, what's simply called as central potential. I mean, there are few more methods which are utilized to carry out the problem of many electron atoms. One among them is a semi-classical method of Thomas Fermi, and there is a more precise, there's a more accurate, more appropriate approximation used, what's called as Hartree-Fock or self-consistent field method, and these kinds of things can be used to have some knowledge of these many electron atoms. I mean, for electrons at two extreme positions, I mean, what we have here is that we can have electrons, we can have electron. If we have a nucleus, we have a chosen electron, then we have the distribution of the rest of electrons. Now, this distribution and the position of the electron from the nucleus, these things can be exploited to get some knowledge about such kind of many electron atoms. So what we expect here is that we can have a situation where we have electrons close to the nucleus, and we can have a situation where this electron cloud is very far from the nucleus. So we can have some understanding of the system without having the deep knowledge of the electron distribution or the electron dynamics here. Now, to move on from here, we would like to go with very large distance case. First, very large distance case. I mean, when electron of our interest, which we are trying to solve, I mean, the electron of ith state is at very large distance. Say Ri is large. Associated with the remaining n minus 1 electrons. In this case, what we can say is that in this case, what we have is the screening of Coulomb potential of nucleus by the rest of n minus 1 electrons. So they are going to screen the potential of the nucleus, and certainly what we have here as an approximation, if I write down Rij, this Rij can be written as Ri minus Rj, taking their magnitude, and since this the electron is at infinity, it's at large distance from the nucleus. Suppose this is the nucleus, and it's at very large distance from the nucleus, then this can be approximated to Ri. Now, when we do this, we can write down the effective potential V of Ri here. What would be that? That would be simply minus Ze square by 4 pi epsilon naught r, then plus what we will have E squared by 4 pi epsilon naught and sigma. Yeah, what will that sigma contain? That sigma will contain j equal to 1 from 1 to n, but this j cannot be equal to I, times 1 by, instead of Rij, it will be only Ri. Now, so what will be my effective potential in this case? That will be minus Ze squared by 4 pi epsilon naught R plus. So what is this number? This number is nothing but n minus 1. This number is simply n minus 1 by Ri. So what we will have is we'll have E squared by 4 pi epsilon naught uh, n minus 1 by Ri. So we can write down the effective potential for this case when this electron of our interest is very far away from the nucleus. The effective potential for this will be VRI. So we're not writing Rij here. That will be minus E squared by 4 pi epsilon naught. I can get it out. And what I'll remain inside of it is Z plus n minus 1 divided by Ri. So this equation basically represents the effective central potential, and this potential is constituted by the nucleus and other n minus 1 electrons, in which the ith electron is moving independent of other electrons. That will be the case. So it is simply the Coulomb potential of the nucleus that is seen by the ith electron, screened by n minus 1 electrons. Now, we will have another approach that is small distance case. We can have a case here. So when electron that's of our interest, I mean the electron in the ith state, is at very small distance with respect to the nucleus, very close to the nucleus. When I assume it to be very close to the nucleus in comparison to its distance from the other electrons that are acting as cloud in this case. Now, the screening of the Coulomb potential of the nucleus as seen by the electron I due to n minus 1 electrons would be minimum, and we may approximate this Rij in that case, which is basically mod of Ri minus Rj. This can be simply approximated to R of j. And what happens in this case, we can write down the effective potential in this case, say V of Rj can be written here. That will be minus Ze squared by 4 pi epsilon naught R. This is the electrostatic potential energy between the electron of our interest and the nucleus, and that will be added with the screening, that is E squared by 4 pi epsilon naught. And here what we'll have the average. We'll have the average of all that sigma I mean sigma j equals 1 to n, and j is not equal to 1, 1 by R of j. And what we can write down here, we can express this is nothing but merely a number, and we can write down this we can express our central potential for this case as V of R j is minus Ze squared by 4 pi epsilon naught R plus some number, say some number d. And so it is simply the Coulomb potential of nucleus seen by the electron, screened by how many electrons? Screened by n minus 1 electrons. So as Ri, I'll say as Ri approaches 0, in some mathematical sense, that electron is in the innermost orbit, it would just be unscreened by the Coulomb potential of the nucleus, and hence we can express the effective central potential V of Ri as nearly equal to minus E squared by 4 pi epsilon naught times Z plus n minus 1 by R of I for Ri going to infinity. And we will have this V of Ri nearly equal to minus E squared by 4 pi epsilon naught 1 by Rj, as this Rj tends to 0. So determination of this effective central potential at intermediate distances is very difficult. I mean, to have that correlation between the electron of our interest and being the cloud in vicinity of that electron, it's quite difficult to think about and to solve it with the given approach. So why is it so? It's because the intermediate distance. I mean, it would depend only upon the charge distribution of the electron at that time, but also upon the dynamical state of the electrons around the concerned state that we have been talking about. So it's quite obvious, it's quite important here to be noted down that the effective central potential that we have obtained would not account for the complete spectrum, the complete range of complex n electron atoms. But at the same time, if we restrict our interest, if we confine our interest in the ground state or the first few excited states, we may obtain results which are considerably accurate and precise. I mean, if we can have some space for small degree of approximation, many important features of very complex atoms or ions can be obtained by using the expression for effective central potential, the potential that we have obtained, and as the potential is given by these equations. So with this, I would like to end my talk on this central field approximation for many electron systems. I hope you find it useful. I love you all, and hope everybody is fine. So goodbye.